Welcome back to AI Paper Podcasts. Today, we're digging into artificial general intelligence, or AGI. The big challenge really has always been just defining it, hasn't it?
Absolutely. For ages, it felt like, chasing a moving target. Every time AI got good at something complex, people would just say, oh, well, that's not real intelligence.
Right, just narrow AI, very sophisticated, but not general.
Which is a huge issue if you're trying to actually build the thing. You can't build what you can't measure. So this new paper, A Definition of AGI, really tries to tackle that ambiguity.
How do they do it?
They offer a really concrete operational definition. AGI is basically when an AI can match the cognitive range and skill of a well-educated human adult.
And they didn't just pull that out of thin air. It's grounded in solid psychological research.
Exactly. They use the Cattell-Horn-Carroll theory, CHC, which is pretty much the gold standard for mapping human cognitive abilities. This let them create a standardized AGI score, 0 to 100%.
Okay, so the headline numbers. What did they find for current AI?
Well, the results showed what they call a very jagged profile, lots of peaks and valleys. GPT-4, which felt like a massive leap just last year, only scored 27% overall.
27%? Wow. But we know things move fast.
Incredibly fast. They also tested a frontier model. Let's call it GPT-5 for discussion. Its score jumped to 58%.
Okay, 27 to 58% in like one generation. That's a huge jump.
It is. But that 58% also clearly shows how much ground is left to cover. So today we're going to break down the 10 specific cognitive areas they tested based on that CHC model.
And really focus in on those areas where the scores are lagging, right? The bottlenecks holding things back from, true general intelligence.
Precisely. Those zero-score areas are where the real architectural challenges lie. So let's start with that foundation, the CHC theory. Why pick that specific model?
Yeah, why not just test performance on, a bunch of complex tasks?
Because the goal wasn't just if AI could do the task, but how. Does it have the same underlying cognitive toolkit as humans? Or is it just finding clever, computationally cheap workarounds, compensatory strategies, as they call them?
So it's about digging deeper than just task completion. You want to know if the fundamental abilities are there.
Exactly. Simply making large language models bigger might improve performance on some tasks, but human intelligence isn't just one big blob, right? It's structured.
It's got different components working together.
Right. And CHC gives us a map of those components. It breaks intelligence down into broad abilities like fluid reasoning, thinking on your feet, and crystallized intelligence, your stored knowledge. And then it breaks those down into narrower, more specific skills.
So the paper adapted tests, psychometric tests originally designed for humans.
Yep, rigorous tests adapted for AI. And they distilled it all into 10 core cognitive domains.
And importantly, they weighted them equally 10% each. Why was that important?
To prioritize breadth. They didn't want a system to look generally intelligent just because it was amazing at one thing, like language, but terrible at everything else. It forces a holistic assessment.
Makes sense. So what are these 10 domains? Maybe we can group them.
Good idea. First, you've got the sort of core knowledge and basic processing areas, general knowledge, which they label K, reading and writing ability, RW, and mathematical ability, M.
Okay, K, R, W, M. Got it.
Then there's a cluster related to fluid thinking and memory. On-the-spot reasoning, R, working memory, WM, that's like your mental scratch pad, long-term memory storage, MS, and long-term memory retrieval.
R, WM, MS, MISR, memory and reasoning.
Exactly. And finally, the sensory and sort of time-based aspects, visual processing, V, auditory processing, A, and speed, S, which measures reaction time and processing speed.
VAS, vision, sound, and speed. So 10 distinct areas, equally weighted, tested rigorously. That sets the stage for seeing where the current tech shines and where it, doesn't.
Precisely. It gives us a diagnostic tool to pinpoint the real weaknesses.
All right, let's talk about that 58% for GPT-5. Where are these models actually doing really well? Seems like it's mostly in areas that benefit hugely from all that training data.
That's definitely the pattern. And the most dramatic improvement they saw was in mathematical ability. Remember how GPT-4 often struggled with precise calculations or multi-step reasoning?
Oh, yeah. Lots of benchmark failures, especially in things like competitive math or higher level calculus. It scored. What was it?
Only 4% proficiency in the math domain for GPT-4. Really low.
So did GPT-5 make the kind of leap we've been hearing about anecdotally?
A monumental leap. GPT-5 hit the full 10% proficiency.
10%, so perfect score in that domain.
According to their proficiency benchmarks, yes. They tested across 5 sub-areas: arithmetic, algebra, geometry, probability, and calculus, using problems geared towards like an undergraduate level. Getting 10% means it showed competence across the board.
Wow, so it completely closed the gap where GPT-4 basically got 0 in areas like calculus.
That's right. It suggests a really significant improvement in symbolic manipulation and actually following complex steps. It's not just pattern matching language anymore.
Okay, that's math. What about reading and writing, RW? Similar story.
Very similar. GPT-4 was already decent at 6%, but it had issues with, fine-grained meaning at the token level, needing smaller contexts, and it wasn't great at careful proofreading.
And GPT-5.
Also hit the full 10% proficiency. It seems to have overcome those earlier limitations. It demonstrated competence in everything from basic letter word ability up to complex reading comprehension on whole documents, plus sophisticated grammar and usage.
So basically human-level competence in core language skills.
That's what the 10% score suggests, yes.
And the last one in this strong group is general knowledge, Kay.
Right. Here the jump was smaller, but still strong. GPT-4 got 8%. GPT-5 nudged that up to 9%.
Still very high. And this covers facts, common sense.
Yeah, things like basic physics. What happens if you drop a glass bottle on concrete? Plus, science, history, culture. It's your classic crystallized knowledge.
And this really shows the power of just scaling up the training data, right? More data equals more knowledge.
It seems to translate almost directly, yeah. For these knowledge-heavy domains, scale is incredibly effective. Okay, but now we get to the other side of the coin, the jagged part of the profile. This is where we see those fundamental gaps, sometimes with scores hitting absolute 0.
0%. That's stark. Where's the biggest hole?
The most critical one, architecturally speaking, is probably long-term memory storage, MS. Both GPT-4 and GPT-5 scored 0%, flat 0.
Hold on, 0. But these models can remember things within a conversation, right? They have context windows. How can they score 0 on memory storage?
But that's working memory, WM, or just context window retention. MS is different. It's the ability to stably acquire new information from experiences, consolidate it, and store it reliably for later use.
Like learning someone's name and remembering it tomorrow, or remembering the plot of a book you finished last week.
Exactly. Associative memory, meaningful memory, even verbatim memory, like remembering a phone number perfectly. The 0 score means they fundamentally lack this ability. They suffer from, amnesia.
So they can't actually learn from interactions in a lasting way. Every time you start a new chat or the context window resets, it's like they have amnesia.
Precisely. Which really limits their usefulness for anything requiring continuity over time, like a personalized assistant. And it's computationally wasteful to keep refeeding context.
Okay, 0 on memory storage. That's huge. What's next?
Directly related is long-term memory retrieval.
Victor.
This is where we quantify the hallucination problem.
Okay. This is about accessing the knowledge they do have or think they have. What were the scores?
Only 4% proficiency for both GPT-4 and GPT-5.
4%. Better than 0, but still very low. Why?
Well, they actually score perfectly fine on retrieval fluency. That's just generating ideas quickly, like brainstorming. They get the full 4% on subtasks like ideational fluency or word fluency.
So they can spit out related concepts easily.
Yes, but where they score 0% is on retrieval precision. That's the ability to retrieve accurately and, crucially, avoid making things up confabulation.
The hallucination part.
Exactly. The paper had a great example. They asked the models to describe the key strategy that Napoleon Bonaparte used to win his South African campaign.
Which never happened.
Right. A human or an AI with retrieval precision would say, hold on, Napoleon never fought in South Africa. But these systems, they often just generate plausible sounding nonsense about it.
Because they're predicting likely word sequences, not checking against a stable, factual knowledge base or, reality.
Precisely. They lack that grounding.
Okay, so major memory issues, both storage and retrieval precision. What about reasoning? On-the-spot reasoning are...
This is where we saw the second biggest jump after math. GPT-4 scored 0% here across the board. Deduction, induction, theory of mind, just nothing.
But GPT-5?
GPT-5 jumped to 7% proficiency,
Right.
which is significant progress.
Where did it make gains?
It showed real competence in deduction, solving complex logic problems with multiple premises. They give an example about figuring out relative ages. And it also improved a lot in theory of mind, understanding other people's mental states.
Like the example about knowing if Mary knew the Pringles were moldy.
Yeah, exactly. Inferring what someone else knows or doesn't know based on context, that's a big step for social reasoning.
But it's still only 7 out of 10%. Where's the remaining gap?
The critical failure point is adaptation. GPT-5 still scored 0% here.
Adaptation, what does that mean?
It's the ability to figure out new rules or categories on the fly, and maybe more importantly, to abandon old rules when the situation changes. Think of the Wisconsin card sorting test. You have to figure out the sorting rule, then suddenly the rule changes, and you have to adapt.
And GPT-5 can't do that flexibly.
Apparently not. It can learn rules, but struggles profoundly to unlearn them or switch strategies fluidly when the context demands it. That's a core part of fluid intelligence.
Right. Okay, so memory and adaptation are major sticking points. What about the senses, vision, and auditory?
Yeah, multimodality is still nascent. GPT-4 was at 0% for both visual V and auditory A. GPT-5 showed some real, though incomplete, progress.
What were the scores?
4% in visual processing. So it's starting to handle some basic perception and generation tasks. And 6% in auditory processing, which seems mostly driven by good speech recognition.
But still gaps there, too.
Oh, definitely. On the auditory side, things like phonetic coding, understanding rhythm, judging music, those are still weak.
And this all ties into the final domain, speed, S.
Exactly. Both models scored only 3% on speed.
Why so low if they can process text quickly?
Because speed here includes reaction time and comparison speed, especially on those harder multimodal tasks. If you ask it to quickly perceive and react to a complex visual scene or sound, its thinking time is apparently way too slow compared to human baselines. That lag penalizes the overall speed score heavily.
Got it. So while they're fast at some things, the overall interaction speed, especially with complex inputs, is still far from human level. So putting this all together, the paper paints a picture of AI that's incredibly powerful in some ways, but fundamentally broken in others. I like the engine analogy they use.
Yeah, the idea that the overall horsepower of the engine general intelligence is limited by its weakest parts. And right now, critical components like memory storage, MS, and that adaptation part of reasoning are basically defective, 0% functioning.
And this forces developers into workarounds, right? What the paper calls capability contortions, clever tricks to hide the weaknesses.
Exactly. Ways to create an illusion of generality without actually having the underlying machinery.
The most obvious one seems to be using enormous context windows, essentially. Massive working memory, WM, to make up for the fact that there's no real long-term memory storage, MS.
Right. If you can keep the entire interaction history or even huge documents in active memory, it looks like the model remembers. But it's incredibly computationally expensive.
And it doesn't scale, does it? You can't keep weeks or months of context live.
No way. It's a temporary fix, a patch. It doesn't solve the underlying amnesia problem.
Yeah.
The paper suggests real MS might need fundamentally different architectures, maybe dynamic modules like LoRi that constantly update based on experience, actually changing the model.
That makes sense. But I do want to push back a bit on the methodology here, or at least the weighting.
Okay.
If GPT-5 can hit 10% in math and 9% in knowledge, skills that seem to scale really well with current methods, doesn't giving just 10% to something like adaptation, which seems architecturally much harder and maybe less scalable right now, bias the score against the kind of AI we're actually building?
That's a fair point and a really important discussion. The researchers would argue, I think, that their framework is deliberately human-centric. The goal is to measure against the breadth of human cognition.
So equal weighting forces developers to tackle the hard stuff.
Exactly. If you defined AGI based mostly on skills that scale easily with data and compute, like map or knowledge recall, you get a high score quickly, but you wouldn't necessarily have general intelligence in the human sense. You might just have a very powerful but still narrow system.
So the equal weighting is a way to avoid moving the goalposts again by insisting that all core human abilities need to be present.
Right. It highlights the difference between building something that's cognitively general versus something that's just economically valuable. You could build an AI that makes billions, maybe in drug discovery or coding, but if it still has zero long-term memory or can't adapt to novel situations, under this definition, it's not AGI.
That distinction is key. Okay, so the context window is one contortion. What's the other main one?
Retrieval augmented generation, or RAG, using external databases or search tools to fetch information on the fly.
Which helps massively with the hallucination problem, the lack of retrieval precision, MR.
It does. It's a clever engineering solution. But again, it's a contortion masking an architectural flaw. Well, first, it hides the fact that the model itself can't reliably access its own internal static knowledge encoded in its parameters. But maybe more importantly, RAG is about retrieving external facts. It does nothing to solve the lack of a dynamic experiential memory, the kind needed for true personalization or learning from unique interactions.
So RA pulls from a database. It doesn't build a personal memory trace.
Precisely. It's not a substitute for an integrated, continuously learning mind. It's another clever workaround.
Okay, so quite a journey. We've seen this leap from 27% for GPT-4 to 58% for GPT-5, driven largely by mastering those highly scalable domains: math, reading, knowledge.
Huge progress there, definitely.
If these scores really quantify the massive gaps that remain, the problems aren't just about making things slightly better, they're about fundamental cognitive machinery that's still missing or broken.
Yeah, the path to 100% to true AGI by this definition means cracking these grand challenges, the things stuck at or near zero, getting robust continual learning and memory storage,
Yeah.
MSET, achieving true abstract reasoning and adaptation, R, and developing fast integrated multimodal processing and speed, S.
It's not just about scaling up what works now, it requires architectural breakthroughs in these specific bottleneck areas.
Absolutely. So maybe a final thought for you listening, especially if you're working in this space, looking at those three big zero-score bottlenecks: long-term memory storage, reasoning adaptation, and multimodal speed. Which one do you think represents the toughest nut to crack? Considering how quickly math was solved, which of these remaining grand challenges feels like the biggest, most fundamental barrier on the path to 100%? Something to mull over.